Today's lesson is on Lewis structures. Gilbert Lewis gave us this model to help us understand molecular bonding and bonding between nonmetals. So with Lewis structures, we use dots to represent non-bonding electrons and dashes to represent bonding electrons. We're only going to be showing our valence electrons since those are the electrons that participate in bonding. Now, most of you have already copied this part of the notes down, so I'm going to breeze through this really quickly and try to get to the examples. But the rules for writing Lewis structures, of course, you want to have your periodic table handy, is you're going to add up or sum up the valence electrons for all atoms in the compound. If it's a polyatomic anion, remember you're going to add 1 electron for each negative charge. And if it's a polyatomic cation, you have to remember to subtract 1 electron for each positive charge. We're going to use PCl3 as our example as I go through the notes today. So phosphorus is in group 5A. He has 5 valence electrons. There's 3 chlorines, and each chlorine has 7 valence electrons. So 5 plus 21 gives you 26 total valence electrons that will be used for bonding. The central atom here is going to be your least electronegative element that isn't hydrogen. Hydrogen typically goes on the outside, remember, because it follows the duet rule. You're going to connect the outer atoms to the central atom. Initially start by single bonds, dashed lines. So remember, a dashed line here represents 2 electrons being shared between the atoms. Keep track of your electrons. So here we've connected the 3 chlorines to the central phosphorus, and that's 2, 4, 6 electrons that we've used so far. So we say 26 minus 6 gives us 20 electrons that we still have to use. Next, you're going to fill the octets for the outer atoms, except for hydrogen. Remember, he follows the duet rule, but we don't have hydrogen here to worry about. So again, we had 20 electrons remaining, and so we're going to place them around the outer atoms first. So 2, 4, 6, 8, 10, 12, 14, 16, 18 is what we have when we distribute them, and that gives all the chlorines their octet. And we have 2 remaining, so they're going to end up going on the phosphorus because phosphorus still needs his octet, 2, 4, 6, 8, so the remaining 2 go above phosphorus. If you happen to run out of electrons before the central atom has its octet, that's when you will want to form multiple bonds. So form multiple bonds until each element have their octet. Remember, fluorine, oxygen, nitrogen, and carbon will always follow the octet rule. There are some exceptions to the octet rule, but these elements always follow the octet rule. So here with the hydrogen cyanide, we would have run into the problem of not getting the full octet for the carbon. So these lone pairs that nitrogen has, he's going to swing them down to complete carbon's octet. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. An octet of electrons consists of a full S and P subshell in your atom. There are many exceptions to the octet rule, but it does provide for a useful framework for many of our important concepts in bonding. Boron and beryllium tend to be satisfied with less than 8 electrons because they have very low electronegativities. They are very reactive due to this property. Elements in the 3rd period and beyond tend to exceed the octet rule. Why? Well, that's because they have empty d orbitals. So here I have abbreviated, but that's EMPTY. They're empty d orbitals that can accommodate extra electrons. If you look at your periodic table, you will find that these elements, that's when your d block comes in the 3rd period. So it's kind of like empty rooms there that can accommodate extra electrons. This is called an expanded octet. This is only going to happen with elements in the 3rd period and beyond. So let's look at some examples. So I have 8 examples here. Let's look at the methane first. So you're going to add up your valence electrons. Carbon has 4. there are 4 hydrogens and they have 1 apiece. That gives us 8 total electrons. So for the Lewis structure, you would start carbon goes in the middle. He's your least electronegative element except for hydrogen. You're going to connect your 4 hydrogens to the carbon with a single bond. So you have 2, 4, 6, 8 electrons that you've used. So 8 minus 8 leaves you with no more. So hydrogen follows the duet rule, remember? So the hydrogens are all happy and the carbon has 2, 4, 6, 8, so he is satisfied as well. In the next one, we have carbon again, so he has 4 valence electrons because he's in group 4A. You have 4 fluorines. Now the fluorines have 7 valence electrons. That gives you 4 plus 28, which is a total of 32 electrons that will be used here for bonding. So for number 2, you're going to connect your carbon to the 4 fluorines with a single bond. That's 2, 4, 6, 8 electrons. So 32 minus 8, that's going to leave you with a total of 24 electrons that you still have to place. Now notice carbon already has its octet, so you're going to put the remaining lone pairs around your fluorines. Each fluorine needs 6 more apiece to complete their octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That completes your octet for the fluorines, so now everyone is satisfied. For number 3, we have a polyatomic ion. Nitrogen is in group 5A, he has 5 valence electrons. Oxygen is in group 6A, it has 6 valence electrons. The positive 1 charge means that it has lost 1 electron. So that gives us 11 minus 1, which is 10 total electrons that will be used in bonding here. So for number 3, you're going to connect the nitrogen to the oxygen with a single bond. And now let's start surrounding the nitrogen with the remaining electrons. So we have 2 that we've used. That means we have 8 lone pairs to place. So 2, 4, 6, 8. Now, we have used all 8 of the electrons that we had remaining. We put 10 electrons out. So this is an instance where we have run out of electrons, and we need to make sure we fulfill the octet for everybody. Nitrogen has 2, 4, 6, 8. Oxygen has 2, 4. So you're going to take from the element that has its plenty of electrons and swing and share. So swing those 2 down. We're going to swing these 2 up. So that's going to leave a triple bond between the nitrogen and the oxygen. So the 2 that we did not swing from the nitrogen remain on him, and then the 2 that were on the oxygen are here. Now remember, when it's a polyatomic ion, you're going to put brackets and the charge around your final structure. All right. Number 4, boron is in group 3A. He has 3 valence electrons. Fluorine has 7 each. That gives you 3 plus 21, which is 24 electrons total that will be used in bonding here. So for number 4, the boron is surrounded by 3 fluorines. That's 2, 4, 6. That's going to leave us 18 electrons to place. Start around your fluorines, 2, 4, 6, 8, 10, 12, 14, 16, 18. We have depleted our supply of electrons. Check for the octet rule. Remember, boron is the exception. He is so weakly electronegative, he's not going to be able to swing any from the fluorines, so this actually remains your structure for boron trifluoride. This is a very reactive substance due to the lack of the octet for the boron. All right, let's continue on. Number 5. Sulfur has 6 valence electrons. There's 6 fluorines, and they have 7 apiece. That gives you 6 plus 42, which is 48 electrons. So we have 6 fluorines to attach. So rather than our normal 4, this is an expanded octet situation. So we're going to put 6 around the sulfur. 1, 2, 3, 4, 5, and 6. Remember, sulfur is in the third period, so elements in the third period and beyond can accommodate extra electrons. We've used 2, 4, 6, 8, 10, 12. So 48 minus 12 gives you 36 electrons that we still need to place. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. And we have exactly enough to give the fluorines their octet. Sulfur has its expanded octet. This is the structure for sulfur hexafluoride. All right, let's look at number 6. Phosphorus is in group 5A. You have 5 chlorines. They have 7 apiece. That gives you 5 plus 35, which is 40 electrons. Phosphorus is also in the third period, so it can accommodate extra electrons, which is going to happen here as well. So start with your original 4 sides, and we have 5 chlorines to place, so put one more on the phosphorus. So Cl, Cl, Cl. So we have our chlorines around. 2, 4, 6, 8, 10. So 40 minus 10 means I have 30 electrons I still need to place. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. And that's the magic number. That's all electrons distributed. Chlorines have their octet. Phosphorus has his expanded octet. All right, number 7 is an oxyacid. So with oxyacids, the hydrogens go on an oxygen. Always remember that. So we have 2 from the hydrogens plus 6 from the sulfur plus 4 times 6 for the oxygens. That's going to give us 8 plus 24, which gives us a total of 32 electrons. Put your sulfur down first, and you're going to connect your 4 oxygens to it. Now, you might be thinking, can I do an expanded octet here? You normally could, however, with an oxyacid, hydrogens must go on an oxygen. So we have to place the hydrogens on an oxygen since this is an oxyacid. 2, 4, 6, 8, 10, 12. We've used 12 of our electrons. That means we have 20 remaining. Now, hydrogen's duet rule has been satisfied. Sulfur's octet rule is satisfied. So that means all the remaining electrons go on the oxygens. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And that's all the electrons. And that is going to complete the octets for the oxygens too. So you're done with that structure. All right, our last example, number 8, you have 5 from the nitrogens. You have 3 oxygens, they have 6 apiece, and here we have a -1 charge. That means we're going to add one more electron. So that gives us 5 plus 18 plus 1, which is going to give us 6 plus 18, which is 24 electrons. All right, your nitrogen comes down first, and we have 3 oxygens to place on the nitrogen. 2, 4, 6. I've used 6 electrons. That leaves me with 18 that I still have to place. 2, 4, 6, 8, 10, 12, 14, 16, 18. And I've used all 18 electrons. Notice you want to double check the octet rule. Oxygen has 8, 8, and 8, but look at nitrogen. He only has 6. So pick an oxygen, does not matter which one. They're all technically equivalent, but you're going to swing a pair down so you have a double bond. So your final structure should have a double bond between one of the nitrogens and one of the oxygens, and the other two oxygens have single bonds. So remember, these molecules are able to move around, so if you turn the molecule, this is fine. It does not matter the perspective you're looking at. But that's what your nitrogen would look like. That gives him his octet. The oxygens that did not share any with him have their remaining 6 dots around them. And the oxygen that did share has only 4 lone pairs, or 4 dots around it. Since this is a polyatomic ion, don't forget to bracket it off and put the charge. Okay, that's it for Lewis structures lesson for today. We'll talk about resonance and formal charge next, and then we will look at the Vesper theory and how to classify the shapes of the molecules in a future lesson.